I would like to welcome you all to this first lecture of this academic year. I would like also to thank Agilent Technologies that have been sponsoring this lecture series since the start in 2006. Before I introduce our speaker, let me mention that 2 weeks from now, we have Dr. Jack Wu. He's an assistant professor in fact, our department. He has recently joined, and he'll be talking about the low-power CMOS circuits for biological applications. And I bet it's going to be a very interesting one, and you'll enjoy it. Our guest speaker for today is Mr. John Harmon, and the title of his talk is Wireless Communication, where is it all headed? Mr. John Harmon is a wireless R&D business development manager for Agilent Technologies Incorporated, based in Santa Rosa. In his 31 years with Hewlett-Packard and Agilent, he has held various positions in research and development, manufacturing, marketing, and business development. He currently focuses on the 4th generation cellular technologies, and he holds a Bachelor of Science degree in Mechanical Engineering from Washington State University. So here is Mr. John Harmon.
Well, always getting my slides up. Thank you very much. That sounds a lot more impressive when I listen to it, actually. It just means I can't really keep a job. That's what it means. So let me first of all welcome you all, and thank you for letting me have a chance to talk to you a little bit. I'm going to try and cover a lot of territory today, and so. Hopefully you can keep up with the change of topics on a regular basis. I'm not going to go too deep on any one thing, but I'd like to keep this as informal as I can. And so if you have any questions, please stop me and ask me if you have anything you want to talk about. As Ollie said, I'm actually a business development manager, so I work in our sales organization, but I've held positions in different parts of the organization. So one of the things that I've enjoyed is seeing a broad spectrum of what we do down in the details of how we engineer things, all the way up to how customers actually use them and where they're applicable. And so that gives me a little bit of perspective that not too many people get the opportunity for. So that's been a great experience for me. Okay, so how many of you are confused by the term generation, or the G? We have 4G devices now. People are talking about all these things. So I'll see if I can clear up some of that. It gets thrown around a lot. This is probably more the marketing hype aspect of generations of devices, but we'll see if we can put a little light on that. Secondly, I just want to warn you that I am going to go into some technology concepts. So if you still have a blinking 12 on your VCR, then we're probably going to have a problem today. But if you can follow along with some concepts, I'm actually like to keep things very simple. I'm a simple-minded person. And to me, if you can't explain something in about 15 minutes, then you probably don't understand it. So I'll try and keep that at that level. Secondly, I tend to use system analogies. Physical systems have a lot of analogous comparisons across different domains and different structures. So it's kind of easy to grab onto things that way. So I'll see if I can keep up with that. Again, if you have any questions, please let me know. And we are going to talk about numbers, so just my little humor for the day. Okay, let's start out with some basics. First of all, wireless communications have been around for a long time. It doesn't necessarily mean it has to be electrical or electronics involved. So this has been happening for a while. What's happened, though, is we've gone from doing directly digital kinds of communication like smoke signals, like semaphores. These little flagmen here are things that people used to still do on ships, but sometimes they used to do it from hillside to hillside to put flags up and things like that. to Morse code, and we actually converted that to wireless when Mr. Marconi figured out how to do that. So there are a lot of evolution. This has been around for centuries. It isn't a new thing in the last 10 years. Secondly, is we're going to deal with fields and waves. This is how this is transmitted through the ether. It's got to make its way through some medium. In the same way that my voice is traveling by exciting molecules and vibrating and spreads it through the air, it needs a physical medium to do that. We're going to use actually electrons in atoms and excite them both in electrical and a magnetic field. And they have a lot of analogies that way. They have some real limitations, but they have a whole lot of strengths to them that we try and exploit. So one of the things I always say about this is scientists and engineers spend their lifetime trying to understand how the world and nature works. And if we're lucky, we get to use it to our advantage. But we don't really invent anything. It's all been there. We're just trying to figure out how it works and try and capture it a little bit. So we're, typically this is an exploration and being humbled by the fact that this is the way nature works. Okay, the other thing I'm going to introduce you to is some different aspects of this. It's not just a technology thing, but there are what I refer to as steep factors. This isn't my term. This is something that's standardly used in business and marketing. A guy named Phil Kotler actually came up with this concept. So this is social, technical, economic, environmental, and political aspects of things. And I'll explain a little bit how that works. Some of that has direct bearing on why we do things the way we do them. Sometimes why are they more confusing and complicated than they really need to be, depending on your point of view. So the first thing I'm going to start out with is we can't do any of this stuff in wireless without spectrum. Our ability to understand how the frequency spectrum works, how do we govern it, what are the rules for it, both the physics rules and the political rules. So it's a political owned piece of real estate is the way to think about it. It has an owner. It's leased to different people. Sometimes it's leased as a public domain in an unlicensed band, and I'll explain that. But then there are other industry consortia and organizations that get together and try and figure out how to collaborate on it to make sure we can work right together. It's coming up with our own languages and our own ways of doing protocol, of handshaking, meeting and greeting, connecting, disconnecting. All the same things we deal with socially. In our country, in the US, and every country has its own governing body, we divide up our frequency spectrum and allocate it. This is actually the chart of the FCC. This goes all the way from 3 kilohertz at the very top. This is a logarithmic scale, so it gets, each of these is increasingly farther along in dimension. Goes all the way up to, what is that, Don? 30 gigahertz, 300 gigahertz. So it gets up from 3,000 cycles up to 300 billion cycles. So it's a lot of territory to cover. You can see they've carved it up quite a bit. It's like zoning. You can put an apartment building here, but this is single family residence. This is commercial. This is public park. That's how it's all divided up. Okay? And just to look at a little broader part of the electromagnetic spectrum, this is from very low frequency all the way up to light and X-rays and cosmic rays. So you can see the radio spectrum is only a part of that. So again, this is a little bit of the awesome of nature is you to figure out, there's a whole lot of stuff going out there. Okay, let me bring us back down to a little more microscopic level. So this is the way our current wireless communications is divided up. And I'm going to put it into 2 categories. One is licensed spectrum, and one's unlicensed. Let me explain what that is. Licensed is literally a piece of property and spectrum that you buy. So the AT&Ts and Verizons, T-Mobiles, Vodafone, China Mobile, all these different service providers actually get a license for spectrum from their respective country. And then they have to put a certain service into it. Now the FCC in this country will dictate what sort of service can go into that from a proposal that they make in bidding it. It's got to get bidded on, so they spend money. These can cost many billions of dollars just for the right to build. So it's like buying a lot and saying, before I even put anything on it, I have to spend a lot of money. Secondly, there are unlicensed spectrum. These are ones that are allotted as public spaces. They're a lot like a public park. So nobody owns it except the government has responsibility for it. You can interact in it. If you misbehave, you're asked to leave. But there aren't a whole lot of rules. You don't have exclusive rights to it. So there are some downsides to that. If you buy a license for licensed spectrum, you have exclusive rights to it. You have the right to enforce it, and you have the right to ask the FCC to come in and enforce it for you. So those are the kind of two bifurcations of that. Everything on this side of this pale green color is actually licensed technology. And these are the different generations of what we refer to as cellular phones. So we used to have analog phones, which are first generation. Second generation is we went digital. We had a bunch of standards. GSM and CDMA are still around. So this is AT&T, this is Verizon, is the way to think of it. Then we got some little things where we could put data on things. Got clever about that. These were all voice originally. Then we started adding a little bit more data bandwidth, and we could add things like some video pictures. Nothing really serious, but we could do some interesting stuff. You could do maybe a video telephone call or something like that. Then they started figuring out, gee, this data usage is really getting pretty high. Can we have something that's strictly focused on data? And they did that. That's what 3.5G was. We got that about 4 years ago. And then they went up to 4G, and so now you're hearing about LTE. In some cases, you'll hear about HSPA+. This is high-speed packet access. So the evolution of what's happened is we went from a voice-delivered service digitally down to delivering data, down to converting to what's called a packet network, to now where voice, data, and video are all kind of synonymous with that. It's like having them in a nice little box. They reconstruct it on the other end. And so that's really where we are today. They're actually talking about an even more advanced one now, called Lte-Advanced. So this LTE stands for long-term evolution. Now they have advanced long-term evolution, because they didn't really think far enough on that one. So that's really where the license spectrum is. All this is trying to do is bring you all of these things that you're used to on an ether cable wirelessly. Okay, a lot of problems with that. I'll go into what those are. Second thing is on the license side, this was all driven out of being able to basically convert to a wireless of an internet connection. And so it's always been about basically a computer kind of connection. It's been a packet. It's had protocol to handshake with, but it's never really wanted to do anything like voice and stuff like that until we figured out how to put voice into packets. So that's what you might hear, voice over an internet protocol, or VoIP. So that's what a VoIP call is. It's still not perfect. If you've ever been on a VoIP call, you know it's not great. Skype doesn't really it's not really great audio, but it delivers the goods, and you can do video and things like that on it, and they're getting a whole lot better at it. Tons of research going on, probably even at this university, just about how to process a lot of that. So that's going to progress down to more and more and more. More and more and more. You see kind of where this is going. They used to deliver voice. They used to deliver an Ethernet cable. Now they're trying to both deliver the same thing. So a little bit of a battle going on in that regard. So what's better? So this really becomes a little bit of a Betamax and VHS kind of battle, or is it a compact disc, or is it what's the right thing to deliver this on? So all of these have some varying degrees of freedom on them. All of them have constraints. Not all of them are perfect. In fact, none of them are perfect. But the two genesis things to remember are, this is all stationary. This was never meant to be moving around. It was always based on dealing with Ethernet cable and data and packets originally. This was always a voice legacy, and this was intended to go at high speeds. I mean, driving down the Autobahn at 160 kilometers an hour, or in a train. So these guys never wanted to really deal with that. So those are the two things that they tend to focus on. Okay? Spent a lot of time on that, but that may come in handy as we go along. Second thing we got to deal with is, how do we deal with this spectrum? So it turns out that there's a couple ways. So you think about, how many of you have ever worked an old walkie-talkie? You had to push it, talk, let the button up to listen. Couldn't do it at the same time? Okay, well they actually have a couple different ways of doing this. So we can actually have spectrum that's like a walkie-talkie that way, in that it's called time division duplex. It actually has to, you have to talk and shut up and listen, and then you have to talk again. And so they have spectrum that'll do that. The nice thing is you only need a little bit of spectrum, and you can share that. The downside is you can't shove as much stuff simultaneously. You could have paired spectrum where you can actually have somebody dedicated to talking one way and the other one talking the other way, and you can listen simultaneously. And that's called paired spectrum. Takes up more real estate, but you get a whole lot more effectiveness out of it. So, two different ways to skin that cat. And that's essentially how we look at this stuff. Okay. Third thing is, how do we actually make use of that? It turns out that radio engineers spend an enormous amount of their time architecting things to figure out how to get the most efficiency out of it. How do you cram as much information into a narrow part of spectrum? Remember, that's a lot of money. So the more efficiency you get. So we can do things like divide up radio channels and frequency the same way you divide up your radio band when you're listening. We can also encode on it some time divisioning. Remember, we're packetizing things now, so we don't have to have real time everything. We can actually encode it and then unencode it. So you can have combinations of these. We can do things like code domain. Code domain is kind of a funny one because basically what you do is encode it. So with a code word, and you can simultaneously do, everyone can talk. It would be like in this room, everyone having a conversation. Except each of those conversations were in a completely different language. And your ears, the same way your ears tune out somebody who's speaking Spanish or Russian or German while you're speaking English, these radios can do the same thing. It's a concept called orthogonality. The third thing we can do is we can do some things where we can actually divide up the spectrum and create a whole bunch of individual carriers and put just a little bit of signal on each of those and then reassemble it all at the end. Now, you'll notice this is very simple. This is very complicated. So the first thing is you can't do this unless you have some key components in your radio. A lot of processing. So we go a lot more digital this way, and we get a whole lot more processing going on in order to make that work. And these were not realizable concepts until the last 5 years or so. Okay. I'm not going to go through these, but these are a couple different kinds of service that people can have wirelessly. Most of you know talking on your smartphone or using a wireless LAN connection are two of the big things. Very simple concept of how a transmitter works. So essentially we're going to take information, digitize it, and put it onto, encode it some way and broadcast it out over one of these frequency channels. And we're going to do the same thing when we come back as a receiver. We have to receive it, filter it, convert it, get it down to a point where we can decode it, and then turn it back into what it originally was. It's just the way a radio works. It's pretty magical, but the good thing is the physics on it works. We're also going to do some funny things digitally, and the only reason I want to show you this is because I want you to understand the concept of how we manipulate this a little bit. This is how your AM radio works. It actually just modulates the amplitude, so the loudness of the voice will actually raise and lower this amplitude. And frequency modulation is how your FM dial works. That's what the FM stands for, most of you know. And all that's going to do now is that as your voice goes up and down, we're actually going to make the spectrum get wider, but the variance of this frequency is going to be strictly on the content of the voice that's being done. So a very high-pitched voice would have a lot of closely spaced lines, and narrow ones would not. So now we want to do something digital with it. So we're actually going to encode it. And what we can do is we can create some fairly complex encoding schemes. So the couple things I want you to notice here is that up here we use some very simple concepts of what we refer to as a 1 bit per symbol. So we're only going to have one little binary piece of information dedicated to one of these states that we'll modulate a radio with. But we can actually get some very complex ones where there are a lot more. So I can literally put all of these bits up here for the same amount of spectrum that I'm putting this up. You go, well, why the heck would you do that all the time? The problem is I can differentiate between what these two are. There's a lot of distance between them. Here, I don't have a whole lot of ability here. So you're much more prone to errors. So we refer to that as a signal-to-noise ratio. And the best way to describe that is if I have a very low signal-to-noise ratio, it's really hard for me to discern where something is. So it turns out that there's actually a cross here, but you can't, maybe you can see it. Maybe some of you can see it. The little yellow line there is kind of showing the power level. I'm going to raise that power level up, and now you can start to see it. And now you can see a little bit more. Okay? So the ones where the 2 bits were far apart, I can actually discern that in here. The one where I had those 5 bits per symbol, I really need a power ratio like this. So what does that mean? I need more power. Okay? So that's going to have more demand on the system. So there's an engineering trade-off you've got to make with that. Okay, so all these things conspire against wanting us to be able to have a quality link when we do that. And I won't go through all of these, but the biggest ones we usually have problems with are noise, distortion, and this thing called multipath. And multipath is actually echoes. So think of it as that way. Think if you go into a really boxy room and when you talk, it just kind of echoes off everything and just loudness comes in. That's one of the issues that radios have to worry about. Okay? And then the last one thing I'll show you is that this was 15 years ago. These were all the things that people complained about. What subscribers complained about and what service providers wanted. And there's not a whole lot that's changed except the top one. Notice everyone was focused on voice. Now, actually, your generation is really not speaking a lot. You're more texting more. So I want to be able to see my movies real time. I want to be able to update my Facebook real time. I want to be able to do whatever real time. So what do we do here? What do we do to try and overcome that? So we're going to employ several principles. One of them is we're going to try and just get faster, cheaper, and smaller. And there was a guy named Jeffrey Moore who worked for Intel. His observation at one point was that as they redid a new microprocessor, they could actually they could double the processing speed about every 18 months. And so that's how we were able to get the same power in smaller and smaller and smaller chips. There's some corollaries on Moore's law, often which are abused. But one of them is you can take the same amount of capability and reduce the cost over 18 months by half. Okay? So what would cost you $800 to do 1 year, maybe 18 months would be $400, 18 another months would be $200, and you can see where that goes. So there are a lot of people who invoke Moore's law as an observation about that sort of a trend. But his original observation was we can get more processing power over time because we're learning how to integrate more. There's some physical limits to what Moore's law would allow you to do because you actually get down to the atomic level, but those are all being reached right now. Okay? Second is we'd like to get more frequency spectrum allotted. So this is rezoning the spectrum. So the FCC deals with that on a regular basis. And then the third one is we use a lot of radio techniques, more encryption, different modulation schemes, more encoding, boosting signals, coming up with different ways on how to exploit that. And then lastly is how do we actually transform the whole network? I've only put one down here of internet protocol. The other one is we could change the topology of the network completely. So your cell phone today connects to a base station. Those base stations can be anywhere from right on top of this roof and very close. They can be kilometers apart. They could be miles apart. Or they can be very close. It's what we call shrinking and growing the cell site. They're actually talking about having cell sites that are literally no bigger than this room. And there's reasons for doing that. You can actually divide it up and offload and relay things around. So network topologies is another enabling piece of that. OK. So where is this all going? So I'm going to walk you through a little bit of what my world's like and where I spend a lot of my time trying to understand how this is going to impact things. I'm going to show you each of these slides a little bit bigger format. So one of the things we want to do is kind of look at where have we been. What can we tell from that? So let's talk about what have we learned. So in 2G, what we learned was that scale is a big thing. Okay? People already knew that, but we proved it back to ourselves. And that if you can deliver a low rate, consistent, uniform service, that there's some profit in that. And it can actually enable a lot of people. There are millions and millions of case studies that have been done about how emerging economies have been completely revolutionized by having that. A whole market system has grown out of that, where people never had access to being able to do trade. So there are people who are entrepreneurial and using just a cell phone to go have a living and get something above a subsistence life. The Economist did a wonderful story on that about 5 years ago, just on what the mobile economy is, what it's done in emerging economies. In 3G, what we figured out is if you have a big pipe, that's just not enough. You really do need to be able to get that. You have to have coverage, what's called being able to get it to people everywhere. So the nice big fat pipe that everyone talks about of being able to deliver a lot of data is one of the things we tried to tackle with 3G, but then we ran into the next problem, which is it's got to be coverage. So who ran into that? Who discovered that really in spades? Who got the first iPhone in this room? So, what was the first thing everyone heard about AT&T's network when the iPhone hit the market? That their network sucked, right? Well, the problem was they got deluged with data. Deluged. And the network just wasn't ready for it. So they had the ability to deliver to an individual phone, but they couldn't cover, and they didn't have the capacity in their system to deal with it. That whole dynamic just was not. What that iPhone did was it changed the way you behaved as a consumer, and therefore it demanded something of the network that was not really thought of. So the reaction to that was to create a much better way to deliver that. So now we can do that on a scale basis of a little bit of data, a lot of data to one person. We can change rate structures. We can match it. We have a lot better coverage that we've filled out in a lot of places. And what the problem was is they were also doing data free here. And now we've gotten to the point where, now that you're hooked on this, okay, now you notice people are cutting off. Did you see the headlines about this a couple of weeks ago? They're actually taking the most extreme users and they're gonna cut them off. There's a limit they can go to. So what they're finding is that there are a small percentage of users in their networks that are using a lot of their capacity. So they're not getting a requisite amount of money out of them. So what they're going to do is they're going to limit what they can get. So it's kind of like the guy at the all-you-can-eat buffet, occupying just eating the whole buffet. So they're going to let a few of the rest of us back on there too. So those are the big things that have been learned from this. Okay, so a couple trends. These are all good things because what they do is they raise demand. This ubiquity of wireless and people actually incorporating it into their everyday life. That's the same adoption that internet went through. It's the same adoption that radio went through originally, television went through, so most of the things like that. So it's just become another way that people interact. Okay. So what can we draw from this from a transportation analogy? Some of you have been disrupted by service. I know a lot of people were disrupted when the volcano in Iceland went off, and a lot of us couldn't get home from Europe when we were there for a while. But things like that happen. So let's just look at a couple things. So transportation has evolved over a long time. I'll just go through a little bit of this a little quickly. You really look at what performance is. So this is in our world, in the wireless world, it's really what capacity and what kind of speed can you get. And we also look at basically a varying level of value. We have different things. Sometimes it's I just want a connection. Sometimes I want a really good quality connection. I'm going to watch a movie. I'm going to download something. Sometimes it's I just have a specific thing I need to do, so I've got to be able to have a certain type of connection. My willingness to pay for that, I'm going to give you another analogy. So Coca-Cola, same formula everywhere in the world, right? Wrong. It's completely different. You get a Coke somewhere in another country, it's completely different. It tastes totally different. Why? Because everyone has different tastes. So they've tuned that to all those. They also, depending, you can't buy it for the same price. If I go to an airport, I'll pay $6 for it. I can buy it for 25 cents at some places. Completely different. The kind of service I get associated with that can totally different. So it's commoditized. That's what we call commoditization. And that's really what's happening now. We've gotten to the point where it's no longer novelty. People are expecting it. There's competition, so you have choice. And now it's an integral part of your life. So you have an expectation that it be there. But there's a whole variance on what is acceptable, what kinds of things you want, and what you're willing to pay for it at the time. If you're really desperate, you'll pay $10 for that Coke. Okay, so that's really what. And then the other part is, how much does it really cost to deliver it? The difference between price and cost is usually what we refer to as profit, and that's what makes the world go round in my world. Okay, so let's take a couple look at the extreme version of this. So Virgin Galactica is going to send people through a space plane, right? So you can book your reservation. Well, it's really, that's a pretty high performance thing. So you've got to really understand some of these, and you've got to be able to have an industry that can sustain this. So right now, the wireless industry is struggling with the demand, how to figure out how to properly price things, and how to be able to deliver the right kind of service to people. It's not that they're not making money, it's just that it's an unsustainable model at this point. Okay? And that means we've got broadband everywhere. Okay. Now, part of what you do when you kind of evolve things forward is you usually kind of discharge the legacy stuff. We haven't discharged anything. We've discharged 2 of these formats. So all those things I showed you, we've kept everything. I go around the world, all that exists today, except these 2 things. PDC, which is a Japanese thing, and IS-136, which had a brief history in the US. Everything else still exists. So now, I was just up at AT&T, and they have a whole facility which has nothing but an exact model of every single cell site base station that they've ever put in their network anywhere in the country. So when they get a new mobile, when Apple comes out with a new phone and they want to try it out, they have to try on all of these models. It would be like having every car anyone's ever owned, just to make sure that people can drive it. So imagine that. That's why it takes so long to get these things qualified on a network. But we haven't dispensed with any of the legacy stuff. It's expensive to do. Okay. So I'm going to pop through all these. There's a lot of things that we can look at. One of them would be nice to have one. Let's just have one frequency, one system like GSM, and let's not have all these worries, but the fact of the matter is we need that variety because we have a variety of different things. Plus, that's what innovation comes from, is competition. So what I will tell you is that GSM took off very well. The nice thing was in 1992 we had this completely big political overshadowing event. The Berlin Wall fell. The Cold War stopped. There was a whole lot of free capital in the world. And it just hit that spot perfect. Okay? When UMTS came out in 1999, and what happened about 2 years later? We had a big recession. The big internet bubble hit. Okay? So that had a much more faltering. We're kind of in the same problem here with 4G. We have a kind of a faltering economy. Even though this has taken off pretty well, we expect about the same thing. So let me just give you a couple ideas about how transportation systems tend to evolve and some analogies we can use with wireless of having this legacy to deal with. So here's a good example. This is Denver International Airport. For those of you who know Denver International Airport, what it used to be, it was this huge wide open plain that there was nothing on it but ranch land. So they were able to design the airport exactly the way they can conceive it, with all the runways and capacity and how to figure everything out. It's really nice. It's way the heck out there, but it's very nice. So that's a neat way to do it. So the other way is, and this is all the land that they had, all the different runways. You notice they got 5 runways there. Okay? So now you take a situation where you had a legacy airport and the city grew up around it. This happens to be London Heathrow. So if you start expanding out on that, you see you've got it's really a hodgepodge of terminals. And any of you who've been to London and done the Heathrow Shuffle, you'll know it's a place you'll go out of your way to book a transport somewhere else. It's just a pain in the neck to go through. So this was the first terminal, then the second terminal, then the third terminal, then the fourth terminal, and then the fifth terminal. Okay, they just finished Terminal 5. It's a mess. It really is a mess. It really doesn't look like that from this map, but it is. So one of the problems we have is that we have everyone working on all these different generations. The second thing we've got is we've got people doing all these things that I'm going to walk through here. First of all, we tend to look at peak rates and efficiency in the system. Now this is like buying a car based on how high the speedometer reads. Not how fast it really goes, but how high the speedometer reads. So there's a little bit of, so how many of you ever heard of Guinness World Book of Records? Sure, okay. And who's Guinness?
The guy who makes beer.
So Guinness is an Irish brewery, right? They make stuff, beer that you can eat with a fork. So it turns out that there was another brewery, Macintosh I think it was, and they came up with a book of averages. They figured out what the average was of these different things that Guinness said was the world record of. And in fact, there's quite a gap between the best and the average. And in my world, that gap is growing. The peak performance we can get out of these systems if you tune everything just perfect versus what the average experience of the user is quite stark. So it's something to keep in mind. So we tend to focus on the speedometer reading and not what it really idles out. Secondly, these legacies are not going away. Third is regulators are tending to take a neutral stance on technology. Now, the problem with that is what you end up with is well, we should let the marketplace judge. So that's a way to do it. I'm not advocating one way or the other, but what I'll say is there are consequences of that. Sometimes you get a hodgepodge of things together. If I go to Europe, they decided on one standard, and there are no other possibilities for players, and everything works. I can drive from the very end of the top of Scotland down to the very end of Greece, and I can have a phone call on the same system. On any service provider, it'll hand over. I may pay for it, but it'll work. I can't do that here in the U.S. I've got to be on. If I'm on AT&T service, that's what I'm on. If I'm on Verizon service, that's what I'm on. And if they haven't covered where I want to go, then that's my tough luck. Okay? So there are consequences of that. The other one I wanted to really highlight here is this one. So now there's a couple issues about that, but I noticed one of the lectures we're going to have later on in the series is around lower power CMOS. So this is a big deal. In fact, I would say if you gave everybody in the industry sodium pentothal, what they would tell you, for those of you who don't know what sodium pentothal is, it's called truth serum. They would tell you that power management and battery life is their biggest concern. It is their biggest concern. They can do all this other stuff, but they can't make this stuff dance long enough. Okay, so here you go. We've got all this stuff going on. And imagine if we tried to do a car like this. So you want fuel economy, and yet you want a powerful accelerating engine. You want it really lightweight, but you need it to be really heavy so you get a nice ride and it can avoid a collision. You need to have four-wheel drive, but you don't want to use the power and the weight for all that. So there's a lot of conflicting issues. This is exactly what all the people who design these devices have to figure out, and it's really a hodgepodge of stuff. And we can look at audio and see that people have dispensed with all the old stuff. You don't still see wax rolls around. People have gone to MP3 files. So I'm going to skip through this. This is just about technology adoption. So remember I talked about frequency spectrum? These are all the different bands of frequency spectrum that you can use in the world. In fact, this only shows 41. There are really 45. There have been 4 more added since this slide was created. So now I'm a radio designer, and I've got to design all this stuff to work in all these bands. So it used to be I'd have one radio. And Remember, if I had frequency duplexing, I could do an uplink and a downlink. I could do one way and the other way. Now, I might have multiple radios in there. Okay? And that really gets to be a real bother. Because now you gotta fit all this stuff in. You have to all this duplication of components. My component count goes up. Component count and bill of materials and cost are all directly related. Reliability is all directly related. So it gets a lot more expensive. This is just so you can go from one place to another. From the US to Europe to Japan to China. Okay. So now you're going to end up with a whole bunch of antennas on this thing that have to work. So it's a little bit like carrying around a hedgehog as a phone. Okay, let me take you back down to a little other dimension on here. We have a whole bunch of combination of radios using different parts of the radio spectrum. So let me just give you an idea of this. So these are all antennas that are used for transmitting things to a mobile device. So there's a cell site that's camouflaged as a palm tree. This is a broadcast tower. Turns out for terrestrial broadcasts, so like TV, radio, things like that. This is a satellite, obviously, for doing that. This is a case of a mobile phone, and this is the actual antenna. So they actually integrate it in. So this is a pretty old design. How many of you heard about the thing that happened with the iPhone 4? So it turned out that they put a steel band around that, and that they were going to use that as the antenna. The problem is that people held on to the phone, and your body's conductive, so you became part of the antenna. So when you touch it, it's called detuning the phone. So it doesn't work, and that was one of the problems with it. This is actually a 60 gigahertz device. It's used for transmitting. It replaces the HDMI cable to go from your DVR to a TV. So it transmits very high bandwidth kind of signal. But this is the actual antenna. It's 28 elements right on the IC. So, and it basically has beam steering. So it will pick the best path. So if you walk in front of it, it will bounce off the walls and go somewhere else. It's an active processing in it to do that. So this is pretty simple. I'm showing an iPhone here, but it could be any smartphone really. But right now there can be up to 15 different radios, 41 different bands covered, and 1 million applications that have to run in it. So pretty complex problem that people have to deal with. And these can have anything from FM radio to digital audio broadcast to wireless LAN connections to Bluetooth to just a cell pipe. So the problem is that if you increase the amount of complexity, the dimensions of things, it goes up exponentially. That's just the interaction that happens with systems. And what that does is it just creates a real immense problem. The other problem we have, though, is that we tend to look at these things in the same old way. So we tend to go back to very familiar territory. And so part of the problem in the industry, too, is that they're looking over here when, in fact, the keys have been lost over there. But we know how to do this, and that's where the light's good, and that's what goes on. So my company engages in test and measurement, and one of the things we try and do is identify how to do that sort of thing. So it's a target-rich environment for us, but it's a pretty complex problem. And you can't brute force your answer to it, because you just don't have enough time. There's not enough people to do it. So a lot of times if you try and look at experience, you end up just making the same mistake over again. It also feels like we've kind of gotten to a much more complex system here. So I'm going to skip through this. This is a good example of how the complexity or the paradox of going for peak rates versus the average rates really gives you a distorted view of the world. So here we can actually get pretty high rates now, but the average usage is growing more and more, the gap between that. And that's probably one of the biggest problems people have. If you take that to a linear scale, it looks even worse. You can hardly see the average line down on the bottom there. Okay? So it's what's referred to as the capacity crunch. So now we see this in a lot of other industries. I can point to airplanes that have first class and a bed versus what your reality is and what you experience in coach. What a Formula One race car is versus an average car. What the fashion world has versus something you can pick up at TJ Maxx. So there's a whole lot of examples of how this applies to other industry. So there's a good reason for wanting to stretch your limits that way. I mean, all the things that show up in Formula One cars 20 years ago, 10 years ago, are now pretty standard features in a lot of cars today. Okay. This is just an example of a Swedish operator that's not going to charge by the amount of data that you consume. So this is a variable rate. This happened last year. And I'm going to skip through this. So here is a little bit of the paradox of average performance and peak performance. This is Bugatti on the top and a Tata on the bottom. So the Tata costs a couple $100 and the Bugatti costs $1.5 million. A little bit different in price. But here's the funny thing about it. So you take this beautiful car, isn't it? So here you go. You've got great horsepower, wonderful top speed, 250 miles an hour, great acceleration, great braking power, $1.5 million. If you run it at its top speed, it will empty its gas tank in 12 minutes. Okay? So you kind of have to ask, where would that be applicable? If you put it in the middle of Hong Kong, does it really matter that you have that kind of a car? Other than the prestige of having it. So if you take an iPad 2 and you put it in a really bad network, what you have is a really expensive traffic jam. And that's exactly the kind of problems we run into. So it is a system problem. I want to keep going back to this. These are system level problems that have to get dealt with. Okay. I am going to skip through that because I think I got a little better slide here. This is an interesting slide here. So here is just text messaging. SMS is short message service. That's just technically, as texting. Look how much, if you price it, you're only doing a few bytes at a time, but look at what, 15 cents a message. Look what it costs per megabyte to deliver that, though. If I go all the way up to an advanced 4G device, I can deliver a megabyte for 2/10 of a penny. So the scale of this is changed a lot. So we've been able to get much more efficient in a cost delivery and engineering delivery of that bit, but we had to go through 4 generations to get there. Okay. And I'm sorry I'm squeezing through a lot of this because I know I've run out of time here. So part of this is how do you really figure out what's going to win? And my view of it is you shouldn't worry about what's going to win. What you should worry about is what's going to decide what's going to win. And it's best to look at scenarios and what are inflection points and what are dependencies on that. So you could look at Ethernet topologies versus token ring. You could look at wireless LAN. You could look at Windows. You could look at Iridium, which was a satellite phone system versus a terrestrial phone system like GSM. But if we pursue perfection, the problem we run into is that we never get there. We just never get there. So this is a lesson in the practical implementation of a system level problem. The first point is to get something done and to make it work and then to improve it. But if you sit down and try and design the best system and the perfect system, you're usually going to fail at it. It'll work in your mind really well. That's about as far as it'll get. Okay. So we talked about licensed and unlicensed spectrum. So let me just show you a couple things. So think of Wi-Fi as just like a public toilet. Okay? So its access is cheap. It's increasingly free. But there may be a crowd. And it's not always available when you want it. The quality may vary. And if you've been to a stadium versus a nicer place. It may be out of order or not working. There may be completely different interfaces if you've ever been to the different kinds of public toilets in different countries. You may fear you might catch a virus. And you also are at the mercy of the people around you. So this is one of the things about the public spectrum, is it's noisy and everybody gets to use it. It's not your exclusive right. So one of the problems you can have with wireless LAN, some of you have probably already figured this out, is that if you can be on the same channel and it won't pollute. And that causes a problem. But Wi-Fi, public spectrum usage has grown exponentially. And in fact, it's outdone what's gone on in cellular. So it's here to stay, and how we make it work is really the issue. So what I would say, I'm going to paint all these down here. One of the things we have to look at is the fact that there are good ways to optimize both of those topologies in the system and how to make use of them. What a lot of the service providers today on licensed spectrum are doing is offloading their calls onto Wi-Fi. So if they can be offloaded on Wi-Fi, they're doing that. What they're going to do is they're going to try and retain you, those of you who want to spend money on the cellular service and get the service you want. So it's a little bit like relegating somebody to coach who can handle coach and keeping the people in business class and first class that they want to keep. Okay. I'm going to go through that. So let me just put a couple things down here, and I'm going to paint these out since I don't have time to do that. So I would say that the old focus has been on which generation were we on. And the new focus is really going to be on what Apple's created, which is around the experience. Secondly is, it's not so much should we get this really efficiency out of bits, but really how do we get the high value out of that. And the peak performance is one thing, but average is really what pays the bills. And I would say coexistence here, power, and really getting some of these other attributes involved is really one of the things that's going to happen. Now, some of you may not know this. I'll get into the MTM thing in a second, but I just heard a report on the way over, in fact, that China, the country, is now asking Apple, the company, to be more transparent about which of its factories are actually, which factories in China are actually making its phones and what they're using in them and what the process they have in them. The reason is that their accusation is that the factories that Apple is using, because of the volume of products that they make, is actually poisoning the water system around those factories. And China, because of its growth, and a lot of it because it doesn't have very well organized regulation around that, has a real problem with toxic pollution within their food system and in the water system. So this is one of those little things that rears its ugly head. Remember I talked about steep factors, that's one of those factors. So it's an economic, environmental, and political factor all combined in one. So you're going to hear more of this. Apple's a prominent example because it's such a successful company and such highlighted, and it's got a big bullseye on it because nobody likes to have a super dominant champion in the world. So, but everybody else has the same sort of issues. And you'll see this more and more. Okay, the Internet of Things. So we have all this people communication going on, and we think this is, this is great. There will be, how many people are actually live in the world today?
6 billion.
About 6 billion, right? How many people do you think have a mobile device? Or have made a call on a mobile device?
3
Yes, it's just about 3. I think it's just about half. Maybe a little less than that. Amazingly enough, almost 1 billion people have never made a phone call. Okay? In 2030, I'll put this statistic up in a second, they predict that we will have 50 billion devices talking to other devices, called machine to machine. So that's what M2M is. This is what's referred to as the Internet of Things. So we've taken what was the Internet wired, and we've created a wireless world where it's all connected. So they're putting things, these are kind of 2 obtuse examples, but I will tell you, I went to a presentation a couple of years ago by a guy who runs he's a chief medical officer for a wireless health institute. And they took the 10 top chronic diseases in the country, and things like obesity, things like diabetes, and they figured out what can wireless technology do to help transform that. And one of them is to bring what the phone did to change from when you dialed a number, it was a place because it was wired to the wall. So now you dial a number and you get a person. So now you had to go to the doctor's office. Now the doctor can come to you because they can translate that. So it's going to transform our world, and that's because it's ubiquitous, it's cost effective, and everybody understands it. And it's invisible. It's no longer a technologically cool thing. You expect it to work. It's like the lights going on. So we will see more and more of this. These are other examples. There's a tremendous amount of this stuff going into cars, and there are more cameras delivered through smartphones and mobile devices now than there are standalone cameras. Okay. The other thing is it's changing the economies. So the old guard in the mobile phone world was Nokia, Motorola, and Ericsson. In the new guard, it's Apple, Google, and Microsoft. Okay? And that's because we've changed the way that is. Now, smartphones are really where a lot of the action is. And so they need operating systems, and that's what drives that. And there were other players on that new guard, but for instance, HP just decided last week that they're going to get out of that business. Okay, now, here's an unintended consequence. Does everybody know what the law of unintended consequences is? That's the stuff you didn't think about, but you should have. So now, everyone's suing each other around patent infringement. So Google just bought Motorola's mobile device, and the whole reason they bought it was to get the patents. Several companies went after Nortel when they went bankrupt. So there are a lot of people getting intellectual property, and what the problem is these things have become like trading stamps. So two lawyers walk into a room, one puts a stack of patents this high, and the other one puts a stack of patents this high, and then they start negotiating. And literally what happens is you get trade secrets going back and forth because people exchange things. It's much easier to make a settlement than it is to sue, but nobody can get away with not implementing somebody else's patent on some of this stuff. There's just a lot of stuff patented. Part of it is our archaic system of patents that we have right now and the way the patent office works. And the other part of it is people have realized that there's another way to make money. This company here actually has what I call the one-to-one engineer to lawyer ratio. Okay? And literally their front office is attorneys and their back office is engineers. And that's what their whole value proposition was. They wanted to create technology that was required in order to make that wireless world work, and they wanted to be able to collect revenue off it. And they had to basically be able to stand up and defend it. So they did. Qualcomm's done the same thing, another company. So a lot of these point to Apple. This is just a good example of it, but everybody gets involved in it. You can see all the different players there. Okay. So let me just summarize a couple of things here. So first of all, there is no end in sight to the use of bandwidth, meaning spectrum, meaning capacity in the system. So we're always going to be pushing on all these things. There isn't going to be any insatiable part. I would accuse us now as consumers of having made the smartphone and the wireless devices that are like it the SUV of wireless devices. What were SUVs? SUVs were, I didn't want my father's station wagon because I sure as heck didn't want to be seen in that. But I wasn't willing to give up. I wanted something that looked like a truck, acted like a truck, could carry my family around with a little bit of class, had lots of places to put my stuff. I didn't care how big it was. I didn't care how much energy it consumed. I didn't care what impact it had on the rest of the infrastructure, like parking spaces and roads and everything else. I just didn't care. I wanted more. And we've done that with these. That's exactly what's happening. Now, the price to be paid, the same thing with SUVs, is when the energy crisis hit with gas prices going up. Now everyone's realizing I can't afford to have that much energy usage. I got to get that down. Everyone's trying to re-engineer the applications so they don't suck so much energy. There's a whole lot of engineering going on in that. So those are all good things. Spectrum policy is pretty messed up. It's not going to get a whole lot better, but there has to be some serious rethink on that. And there's a lot of debate in Washington going on that you don't hear about because you're hearing all the debt ceiling stuff. But there is a tremendous amount. I met with a couple guys from the FCC on this, and there's actually a lot of things that are in the works. So we won't see much manifestation of that for about 5 or 10 years, but it needs to get worked on. This is probably the biggest issue right now, and the interaction of the system of both the devices and the networks is a big deal. Literally, people are working on how to say, and rather than putting in multiple radios, how can I actually figure out how to make this radio tune from here all the way up to here? So we're getting things to stretch over multiple applications in some ways. There's a lot of work going on down at the semiconductor level to do that. MEMS technology is a big core component of that. Being able to take things in a higher cost, higher performing semiconductor material down to silicon is the other way to do that. So those are all two things that are happening now. Moore's Law and the misapplication of it is people still believe that that's going to happen. It's just some downward trend that's always going to be there. And I would say there's just a lot of pressure out there on a lot of people. So, okay, so I'm going to conclude there. I've thrown a lot of things at you. I tried to give you some. If it looks like chaos, it is. That's what that world is right now. And I would say it's rife for opportunities in the fact that it needs some fresh thinking, but it's also just got a lot of different problems to solve. So.